In this video, we're going to go through a couple of problems related to steam tables or thermodynamic tables. We're going to see how we can solve different questions related to thermodynamics by the use of steam tables. So I'm just going to dive into it. We've got a question here that states that you've got a two-phase liquid vapor mixture of water that is initially at a pressure and you're heating it up at a fixed volume and you have to find out the quality at the initial stage. So the first thing that we should always do when it comes to solving questions like this is list down the information that is given to you. So if I was to point out the information that is given to me, initially I know that I've got the pressure, which is 30 bars, so that means I could write it in terms of P1, which is given to me as 30 bars. And what other information do I have at the initial state? The second information I've got is that it's a liquid vapor mixture, right? So that's all the information that I've got at the initial state. Besides that, I'm being told that we are heating it at a fixed volume to get to our final state, which is at the critical point. So I've got V1 is equal to V2, so specific volume at 1 is equal to specific volume at 2, and the pressure at 2 is equal to the critical pressure for water. Now, what I should do is that I should try and see how this information looks on a PV diagram or a TV diagram. So if I was to trace this onto a PV diagram, let's say I've got some curve over here. So what I'm being told is that I reach the critical point at state 2. So the critical point is the one right at the tip of these two curves. This is the saturated liquid line. This is the saturated vapor line. When both of these converge, they converge at the critical point. Besides that, I'm being told that V1 is equal to V2. So if I'm indicating this by 2, then V1 is going to be a straight line drop down onto state 1. And over here, what I know is that my pressure is 30 bars, right? And over here, the pressure is critical pressure. So this is the information that is given to me. Now what I can do is I can go and look at the tables now. I cannot start with the initial state because I don't know any other information other than the pressure. So I don't know basically what the quality is or what the specific volume is right now. I would have to find out the specific volume at state 2, and that would be equal to the specific volume at state 1. So to do that, I need to basically go to this pressure, which is the critical pressure. And the way to do it is if you go to table A3, what you will see is that you go down the table all the way. The last entry is going to be that of the critical pressure. And just to confirm this, if you want to confirm this, you can go to table A1. And in the table A1 for water, you can spot which would be the last value in table A1. For water, you can spot what the value of critical pressure is for water. And it's going to be the same as this. So at the critical point, what you will see is that Vf becomes equal to Vg, because this is 3.115 multiplied by 10 to the power minus 3 over here. Okay, so make sure you remember that you've got to multiply by 10 to the power minus 3. And over here you've got this value. They are both exactly the same, right? So usually what we do is that when we are under the dome, right, in this region, then we apply the formula for basically to find out, let's say, a specific volume in terms of quality, 1 minus x into, it is Vf plus x into Vg. This is the formula that we usually apply, right? Because the thing is that when we're at state 1 over here, for this state 1, Vf is at this point, and Vg is at this point. And when we start moving up the dome, so for example, if I get to a point that is here, for this one, the value of Vf moves in towards the point that I'm looking at. And as I keep moving up, so if I was at this point here, these two values would be even closer to the state that I'm looking at. And once I get to the critical point, now this relation is applicable under the dome. And once I get to the critical point, specific volume becomes equal to, you could say either Vf or Vg. It's the same thing. So right now, because I'm looking at state 2 over here, so specific volume at state 2 is going to be equal to either Vf at state 2 or Vg at state 2, which is equal to this value over here in terms of meter cube per kilogram. So now I've identified what V2 is, and because I know what V2 is, so I've got V1 as well now. And now from this equation, if I was to apply this equation for V1, then I would need to find out what Vf is at state 1 and what Vg is at state 1. So what I need to do is I need to go to, in the same table, I need to go to 30 bars. Let's say I go to 30 bars here now. And across 30 bars, what I will see is the value for Vf, which is this one, and the value for Vg, which is this one. And what I need to spot is whether the value that we found out here, 0.003155, whether it is between these two, or if it's greater than this value, Vg, or it's less than this one. If, let's say, just as an assumption, if let's say I was looking at the problem right now, we know that this value is between these two values because this is 1.2165 into 10 to the power minus 3. So this is actually 0.001 something. And obviously 0.003 is greater than 0.001. So that's why this value, so basically our Vf at 1 is less than V1, right? V1 is from here, which is equal to V2. And the value of V1 is less than the value of Vg at 1. So when you have this condition being fulfilled, then that means you're in and under the dome. If, just as an example, if my value of V1 would have been greater than Vg at 1, then what that indicates is that my state actually lies somewhere here, right? Because Vg's value is obviously this one, and if V1 is greater than Vg, then that means it's going to be outside the dome on the right side, somewhere here. That would be V1. And then I would be in the superheated vapor region, and then I would have to use the superheated vapor table. If V1 was less than Vf at state 1, then what that means is that because the value of Vf is here, so then V1 would be on the left side of this curve because it's less than Vf. So then I would be in this region, which is the compressed liquid region. Then I would have to look at the compressed liquid table. So when V1 is between these two values, what that means is Vf at 1 is this point. Vg at 1 is this point. So that means that my value for V1 is somewhere between these two. That means I'm within the dome. So what I'm given in the question that it's liquid vapor mixture, that holds true. Even if this wasn't given to me, that you've got a two-phase liquid vapor mixture. If it was just given to me that water is initially at a pressure of 30 bars, I should be able to identify whether water is a liquid vapor mixture or not at state 1. So because it is, we already know that information, and because I know what V1 is, and I know the value of Vf and Vg, so from this equation here, I can write the value of x1, because right now I'm looking at quality. I'm looking to find out quality at the initial state. So x1 is going to be equal to, I just have to basically simplify this equation, and this would become v1 minus vf divided by vg minus vf. Okay. So now you just go ahead and plug in these values. Make sure you remember that for vf you have to multiply 1.2165 into 10 to the power minus 3. Okay. So then x1 would become 0.0296, and that means a quality of 2.96%. Okay, because quality is given like that. You could just write it in terms of 0.0296. That's good enough. So this is the first question. The second question is going to be a bit similar to it, but instead of 30 bars, we're looking at 33 bars. So obviously, the initial process is the same because that hasn't changed. What we have to do is that obviously we're heating at a fixed volume, critical point is attained. So basically, P2 is equal to critical point, pressure at critical point, which is equal to 220.9 for water. And across this, I can find out the value for a specific volume at 2, which is equal to 0.003155, and V2 is equal to V1 because we're heating at a fixed volume. So the value for V1 is the same. On the PV diagram, let's say I'm still looking at the same state, but instead of at 30 bars now, so this was at, let's say, 30 bars, I'm looking at 33 bars. So somewhere here, let's say, and I've got my state 1 here, my state 2 is here. I know, what else do I know? I've got, so the pressure at state 1 is given to me as 33 bars. And now what I will do is that I will go into the table and I will see that there is no pressure value of 33 bars given to me in here, right? So then that complicates things a little bit for us. And what I will do is that I would have to apply an interpolation scheme in here. I have to interpolate to find out that at pressure of 33 bars, what is the value for Vf here, and what is the value for Vg here. And why am I doing that? Because we saw that to find out x at state 1, I need to work it out in terms of V1, which is found out from here, minus Vf at state 1 divided by Vg at state 1 minus Vf at state 1, specific volumes. And Vg at state 1 and Vf at state 1 is going to be across the pressure at state 1. So across this, I need to find out, basically, the value for Vf and Vg. So I need to find out value for Vf1, which is here, and value for Vg1, which is here. So I have to do two interpolations now in order to do this. And how am I going to do that? So if I want to interpolate for, let's say, Vf1, this is simple application of slope formula here. Basically, y2 minus y1 is equal to x2 minus x1 equals y minus y1 divided by x minus x1. So if I apply that for this one, my y values are basically, because I'm looking at Vf right now, so my y values are these, and my x values are pressures. So y2 minus y1 is going to be 1.2347 into 10 to the power minus 3 minus 1.2165 into 10 to the power minus 3 as well, and divide this entire thing by 35 minus 30, and this is going to be equal to, because I already know what basically the value for this is 1.2347, so 1.2347 and 10 to the power minus 3 minus what I am trying to find, which is Vf, that one, divided by 35 minus the pressure at which I'm trying to find it. So it's at 33 bars, right? And this way, now I've got only one variable that I need to find. I've got one equation from this. I can find out the value of Vf1. And just like this, I'm also going to perform the same thing to find out Vg1. And to do that, I'm going to use this column. And once I've found that out, I just have to plug it in here, and I will have the value for quality. Okay, so when you don't have a value given to you in any table, and whether it's the pressure table or whether it's some other table, you have to interpolate in order for you to find out the values. And then once you find out those values, you can plug them in here. Okay, so that was the second question, kind of the same question, just for a bit of a complicated scenario. And now I'm going to move on to a third question, which is a little more comprehensive, so it will help you with understanding a couple of processes together. So what I'm given is that initially I've got pressure given to me, I've got temperature given to me, so I'm just going to highlight it here instead of writing it down separately. I've got P1 given to me, and I've got T1, which is given to me. And it's a piston-cylinder arrangement, so if I want to draw this, I could do that as well. Basically, I've got piston here, a cylinder, and this piston-cylinder arrangement contains water. Okay, so I've got H2O in here. And you're being told that the water is being cooled at a constant volume, until the temperature is 150 degrees Celsius. So this is basically T2, value for T2. And because it's being cooled at a constant volume, so what that means is that V1 is equal to V2. Specific volume is the same. And what other information do I have? And then the water is being condensed isothermally to a saturated liquid. So that means that T2 is going to be equal to T3 until water becomes a saturated liquid. Okay, so that's one major condition that is given to you, that at state 3 you've got a saturated liquid. And now you have to draw the TV diagram, and then you have to evaluate these expressions. So if I was to, let's say, draw the TV diagram for this, right now I don't really have that much information given to me. So let me just draw this curve. If, let's say, I wanted to draw state 1 right now, what do I need to find out? I need to find out whether my state 1 is under the dome, whether it's on this side, or whether it's in the superheated region. And because I've got pressure information and temperature information given to me at state 1, that means I can go ahead and work it out through the tables and see what information is given to me. So what I'm going to do is that I've got pressure information given to me and temperature, and pressure is 10 bars, so I'm going to go to table A3. And in table A3, across 10 bars, I'm going to spot what the temperature given is, because this temperature gives me the value for the saturated temperature, the saturation temperature. Okay, so what is the saturation temperature? That, let's say, if my state was in the dome anywhere, then it would be on this straight line, because this is what is called TS, saturation temperature. And TS is going to be moving on from the saturated liquid line until the saturated vapor line. If the value of my given temperature is greater than TS at a specified pressure, because this is a constant pressure line, right? So I'm looking at 10 bars. So this is a constant pressure line at 10 bars. This is at 10 bars. And across 10 bars, If, let's say, the given temperature to me would be lower than Ts, then I'm in this region. If the given temperature for me is equal to Ts, then I'm in this region under the dome. If the given temperature is higher than Ts, then I'm in the superheated vapor region. So right now what I see is that T1 is greater than Ts. So I'm somewhere in this region, right? So I've identified that I'm actually, my state 1 is somewhere in this region. And so water is a superheated vapor at state 1. So now what I need to do is that because I know now that my water is a superheated vapor, so I need to go to, instead of table A3, which shows you the properties for saturated water, I need to go to table A4 because that's going to show me the properties of superheated water vapor. And in table A4, I'm going to spot, okay, where's 10 bars? And across 10 bars, I'm going to go to temperature, which is 400 degrees Celsius. And across this, I'm going to see what the value for specific volume is. And that is what I have to find at the initial state. So at the initial state, I've got specific volume given to me, which is 0.3066 meter cube per kilogram. So make sure you write the units here. And what else did I have to find? Specific internal energy, and specific internal energy is 2957.3. So U1, small case, is equal to 2957.3. Again, make sure you write the units next to it. It's kilojoules per kilogram. So I've got state 1 sorted now. So this was at state 1. Now I need to move on to state 2 because I've extracted the relevant information for state 1. And now when I move to state 2, what I see is that the temperature is 150 degrees. The water is being cooled at a constant volume. So basically, V1 is equal to V2. So I've got value of V2 given to me. And now because I've got V2 given to me and I've got temperature, so it's kind of the same situation that we looked at in the previous problem. Now I have to go to table A2 because I've got temperature given to me, not pressure. So I'm going to go to table A2. And in table A2, I'm going to spot the temperature, which is 150 degrees. And across this temperature, first I'm going to spot what the pressure is, which is 4.758. So for state 1, when I've got temperature given to me, this is going to give me the pressure information, which is P2 is equal to 4.758 bars. And I've got basically, I know what V2 is, so I need to find out whether V2 is between VF and VG. Okay, and that's why I'm choosing this pressure P2, because if the value for V2 is between basically VG at 2 and VF at 2, then just look at it on this diagram. I'm at a constant pressure curve, and this is giving me the temperature. So the temperature over here is 150 degrees Celsius, and I have a constant pressure curve, and the constant pressure is 4.758 bars. And now, because I've spotted that V2 is between these two values, so that's why I know that my state 2 is going to be under the dome. If V2 was again greater than VG, then I would be still in the superheated region. But because V2 is between the values of VF and VG, that's why I know that my state 2 is under the dome. So this is my state 2 over here. Okay. And to find out, let's say if I was to find out, because I need to find out the specific internal energy at state 2, so what I need to do is that first I need to find out the quality at 2, which is going to be equal to V2 minus Vf at 2 divided by Vg at 2 minus Vf at 2. And Vf and Vg values are given to me here. V2 I already know is equal to V1, so I can find out the value for quality at state 2 over here. And to find out the value for specific internal energy at state 2, all I have to do is I just have to apply the same formula, which was 1 minus x multiplied by UF at 2 plus x into UG at 2. And again, this information and information for UF and UG is going to be given to me in the table, so I have to read the table in this direction and I have to spot what the values are. Just plug them in. Value of x, x2 is something I already found out, so from here I can find out the value for U2, which is specific internal energy in terms of kilojoules per kilogram. Once I've spotted that, so this was state 2, now I can go on and see what's happening at state 3. Okay, so at state 3 now, one information that's given to me is that the water is being condensed isothermally, so the temperature doesn't change. And the second is that it converts into a saturated liquid. And saturated liquid, this is the saturated liquid line, so that means my state 3 is going to be right on the line. This is my state 3, and it's happening at a constant temperature and a constant pressure as well. So P2 is equal to P3, something I already found out, P2. So P2 is equal to P3, which is 4.758 bars. And what else? I need to find out the value for specific volume at state 3, which is basically going to be equal to now, because I'm right at this point now, so V3 is going to be equal to Vf, because Vf is on the saturated liquid line. So Vf at 150 degrees, right? So that's going to be equal to this value, 1.0905 into 10 to the power minus 3. So I've got the value for V3 as well now. So now all three states are sorted. I've got all the information that I wanted to find out. Now I need to find out the work done in kilojoules per kilogram. And to do that, first we need to see that this process, state 1 to state 2, it's happening at a constant volume. And because right now we're looking at work done only in terms of volume change, so area under the curve is under state 2 to state 3. So this is the only process that is going to give you work done, right? So I don't need to evaluate the work done between state 1 and state 2, which is process 1 to 2. So I just need to go with process 2 to 3. And for that, work done in terms of mass is something we've previously seen in terms of pressure and differential of specific volume. So it's given as PdV integral applied from the initial state, the specific volume at initial state, to specific volume at the final state. And because we're looking at process 2 to 3, so we're looking at specific volume at 2 to specific volume at 3. Because we're looking at a constant pressure process, so pressure term is going to drop out of here. It's going to become P2, and it's going to be multiplied with, when obviously we take the integral for dV, it's going to be converted into specific volume V, and once we apply these limits onto it, it's going to be V3 minus V2, right? So now I know what the value for this is, which is P2 is 4.758 bars. I plug that in here. V3 minus V2 is going to be, in terms of V3 is 1.0905 into 10 to the power minus 3, and V2 is 0.3066. Okay, this is something we saw as well. Did I write it down? Yeah, I did. It's here. So V2 is equal to V1. So I know all these values. Now I just have to be careful with the conversions, because this is in bars and this is in meter cube per kilogram, so I need to convert this. And then to do that, I need to multiply it by 10 to the power 5, and I need to divide it by 10 to the power 3. And once I carry out these calculations, I'm going to find out work done, which is going to come out as minus 145.38 kilojoules per kilogram. Okay. So this is the work that I found out, and the minus sign indicates the direction for the work. And this is how you usually solve a problem that may look complicated, but it's not actually complicated if you start drawing the TV diagram or if you start drawing the PV diagram. So my question to you would be, try drawing the PV diagram for this same problem. See how that works out for you. Okay, and maybe try solving a couple of more questions like this so you get in a little bit of practice.